Okay, this video is to set up to look at Lab 14, Exercise 24, our comparison of DC voltages and AC voltages when we look at them and view them on an oscilloscope. So our basic circuit is a 10 k ohm resistor with a 1 k ohm resistor. They are hooked in series, and in one circuit we're going to supply a DC voltage, the other circuit will supply an AC voltage. So we have a 1/10 relationship here. We should see a 1/10 load drop when we're looking at this R2 will be 1/10 of what we see at R1. So let's take a look at that in Tinkercad. Looking at Tinkercad, here is our circuit setup with a DC power supply. I have two oscilloscopes over here, and here are my resistors. So I have my 1 k ohm resistor here, and I have my 10 k ohm resistor here. It is actually backwards from the schematic in the lab exercise, but our results will be exactly the same. So this is the 10 k ohm, this is the 1 k ohm. And what happens when we simulate this and look on our oscilloscope? Notice as this thing charges up, we're set at 6 volts on our power supply. And our current value here, if you calculate with Ohm's law, is 546 microamps. We're not so concerned about what the total current, circuit current is in here. We're really concerned on what does this look like on the oscilloscope and why does it look that way on the oscilloscope itself. When you look here, the oscilloscopes on the surface look exactly the same, look like identical images. And what we have to do in Tinkercad is you got to zoom in on these oscilloscopes and look. This is the x-axis is the time axis, and the vertical axis, the y-axis, is the voltage. And right now I'm just concerned with voltage. So let's see here. On this oscilloscope here, it says there's a maximum of 2 volts across these 10 squares, or what we call divisions. And that's important to consider as you're looking across these 10 divisions to know exactly what this value is. When I compare that with this oscilloscope over here, it's a much different look. It says I got 20 volts across these 10 divisions. So if I have 10 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares, and I have 20 volts total, 20 divided by 10 means each one of these squares or divisions is worth 2 volts. And respective to the horizontal 0 here, we're going to look and count the number of squares above the 0 axis. And so above this horizontal, we're 1, 2, we're not quite 3 squares coming up our grid here. That difference matches, so this is my 10 k ohm, that's the significant voltage drop. And 1/10 of that we're seeing over here, and that difference matches. So if that's 2 volts to the division, this one over here is 0.2 volts to the division. So let's look at what that looks like. 0.2 plus 0.2 is 0.4, and we're a little more than half here, so we're 0.5. And we're actually about 0.545 if you were to calculate it out. And that's what this graph is showing us here. If you count the number of squares vertically from 0, there's 1 square, 2 squares, not quite 3 squares. 3 squares would be a 0.6 reading, and this is a point, specifically it's going to be 0.5454 volts. The difference is seen right here. So here's our total 6 volts applied. And so what you see in this above our horizontal is 2 volts, 4 volts, 5 volts, and your 5.445 is about what this reading would be, again, if you calculate out the voltage drop difference. Notice the DC voltage on the oscilloscope appears as a straight line. It's a straight line. The current is one direction, and so everything shows up here as one directional. Now let's compare that to what we see in the AC circuit setup. Okay, when we look at the AC circuit, we have the same circuit setup, series connection of our 1K ohm resistor, and then 10 times greater with our 10K ohm resistor right here. Our source this time is a function generator. That function generator is set at a frequency of 500 hertz, an amplitude of 8 volts peak to peak. We have our DC offset set at 0, so our sine wave is going to be splitting the difference on the midline on the oscilloscope here, and our function is a sine wave that we're putting across this. This information is directed in your lab sheet, looking at the Lab 24 lab guidelines. On step 11 there, set your function controls 8 volt peak to peak, 500 hertz sine wave. So as we examine this circuit, we're going to go ahead and simulate this and look at the oscilloscope waveform. Now, on the surface, these look exactly the same, but just like we did in the DC, you're going to have to zoom in and look at the scale along the side there. This one says there's a total of 1 volt for these 10 divisions, meaning each division is equal to 0.1 volts. Okay, so this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1 volt total. So when you split out from the middle here and you're trying to count a peak voltage, you're counting 1 square, 2 squares, 3 squares. It looks like maybe 3.5 squares, or perhaps a little more, just about 3.5 squares. Double that for your peak-to-peak voltage. That's going to be 7 squares, or 0.7 volts peak-to-peak. Okay, it's about 0.73. Now, we look, that's across our 1K ohm resistor. When we look at our 10K ohm resistor, we're going to see 10 times that. So again, over here now our scale is 10 volts in the vertical. So each square or division is equal to 1 volt. If you count from the midway peak voltage, that's 1 volt, 2 volts, 3 volts, a little more than 3.5 volts, just about 3.5 volts. Double that, that's 7. So you're at 7 volts peak to peak here. And then again, it's about 7.3 volts peak to peak there. And you're 0.7 volts or 0.73 volts over here. You add those two together, 7.3 plus 0.7 gives us our 8 volt total that Kirchhoff's law said should be distributed in this series circuit. So you see that Kirchhoff's laws still do apply in our series circuit for AC circuits fundamentals, and our voltage is distributed proportionately by the resistor. We're able to read that on our oscilloscope here. In addition to that, our oscilloscope is fluctuating at 500 cycles per second, or 500 hertz, and we're also able to see that on our oscilloscope where across 10 squares here we're covering 5 milliseconds, and that's on both of our oscilloscopes. So if we're covering 500 milliseconds for the 10 squares, that means each of these squares is equal to a half millisecond. So you can actually gauge the time of the cycle for one full waveform here. If you count across here, we're 2 squares for a half waveform and 2 squares for the second half waveform. That makes sense. You take 1 divided by your frequency to get your period of your waveform. 1 over 500. That is 2 milliseconds. And so you see that here's 1 millisecond, and then 2 more squares. That's 2 milliseconds. So we're able to gauge that also in this lab in terms of the frequency of the waveform. We're going to explore this further and looking at different functions across our circuits here on our function generator. But here we are able to prove Kirchhoff's law in both series circuits for AC and series circuits for DC. You see an equal proportionate distribution of voltage. Okay.